Please welcome Joe Silk.
Thank you, Jim Franco. It's a great pleasure to be here. So I'm going to give you a combination of some historical, more personal reflections and also discuss the future of indirect detection prospects for dark matter. Okay, so up till rather recently, actually, we were sort of convinced that you've heard the motivation for particle physics candidates for dark matter, and there's this wonderful theory called supersymmetry, which is supposed to describe the very early universe, and it has a natural candidate, its lighter stable particle for dark matter, which is predicted to be in a certain mass range of order, some fraction or some multiple of the proton mass. So, and we heard about this WIMP miracle, which so-called, which actually is, it's not particularly accurate or anything like that, but just in the simplest sense, it gives you a very nice prediction because it tells you that this particle with some totally unknown interaction must interact very weakly, not too strongly, not too weakly, and then it gives you exactly the right relic abundance. So this was always very encouraging. However, things have moved on a bit, and now, thanks to the Large Hadron Collider, we have not found any evidence yet for this theory of supersymmetry. And what is more, possibly desperation, possibly just looking broader, the particle physics, astrophysics community has now a much wider stable of possible candidates. And just to mention a couple of them, one is designed to give you this intriguing coincidence in nature, the fact that the dark matter density is of order the same as the ordinary density, and we call this asymmetric dark matter, and that gives us typically a certain mass, about 5 proton masses. And there's another theory, which is the most general theory you can write down for dark matter candidates. It's called the minimal theory, and this gives you a rather more massive candidate of maybe 10,000 proton masses for this weakly interacting dark matter particle. So this is the sort of stable, and there are many others too, but these are the two of the more popular alternatives to our our previous supersymmetric candidate. Anyway, so let me sort of take you back to when I first got interested in the field. First, the motivation, again, more generally to start with. We have, as you heard, also this wonderful connection between dark matter interactions, connecting with standard model particles, so you can both produce standard model particles and therefore see these things in nature, and also you can also use astrophysical situations or terrestrial situations. If you can collide dark matter ordinary particles, you can possibly at high enough energies even make dark matter. And so that would be interesting too, if ever we could do that. And of course, there are many different experimental situations under study now, which include doing experiments you're going to hear about in the next talk, deep underground, particle accelerators like LHC, and then the many indirect detection devices, which include neutrino telescopes, this one deep under ice, and then gamma ray telescopes of various types, both on the Earth and in space. Anyway, so that is the background, really. So how did I begin? Well, and I'm going to focus on indirect detection. So let me take you back then to 1983. So I was in Berkeley. I'd been there a few years. I was building up a small group, and you can recognize some of the people who were postdocs in my group, and we just hired the one on the left, Mark Davis, on the faculty. In the back there is George Eustathiou, Simon, Carlos Frank, and there I am keeping the door open. Okay, so this was an epoch when we were all getting truly excited by the question of what is the dark matter? And most of these guys were doing simulations. The neutrino as the candidate was basically becoming very unpopular with people have been proving it couldn't possibly work or about to. And so what else was there? Okay, so that year there was a workshop at Santa Barbara in the as it was then called, the Institute of Theoretical Physics. And it was designed to tackle dark matter. And it brought together some particle physicists who were stimulated by this challenge, along with many astronomers, pretty much all theorists at the time. And so we spent 2 months in this delightful situation, at Santa Barbara, wandering, long walks along the beach, etc., and thinking and talking and having, we'd have sort of 1 or 2 talks a day to stimulate people, much discussion. And there it became clear that the neutrino was dead as a dark matter candidate. What else could there be? Well, particle physics did have this wonderful possibility, and it was there that I met Mark Srednicki, a particle physicist on the faculty at Santa Barbara, and stimulated by my colleagues who were searching for astronomical simulations that might show how dark matter might or might not work in the universe, we said, well, look, there is this notion that originally came from, again, a paper that you heard about already, by the Lee and Weinberg paper, which suggested that it was a natural candidate to have a dark matter particle from a stable particle left over, a weakly interacting relic from some higher order theory, a natural candidate. So we said, well, if this can occur in the early universe, if this gives birth to these particles, there should possibly be, and then there were the particles created, and also meant it was in thermal equilibrium once, at the very high temperature, so it could both create and be destroyed. Therefore, this process, which occurred rapidly then, and then the particles suddenly, as the temperature cooled down, we left behind with some particles, okay? So we reasoned that, well, maybe out there in the vast depths of our galactic halo, all this space around us, there could be occasional collisions between these dark matter particles, and every now and then they might actually annihilate with each other, as they once did, in extreme conditions in the early universe. And if they did, well, then you could maybe see something. And so this is what came out of our deliberations. In 1984, we said, well, at that time, there'd been a balloon experiment which had measured in the cosmic rays an antiproton, so they claimed, one single antiproton. And it was very controversial, one of these, rare events. But we had realized that if you did have some sort of annihilation going on from dark matter, then it would produce equal numbers of particles and antiparticles, both protons and antiprotons. And therefore, although cosmic rays mostly were protons, if you could look for the rare ones, the rare antiparticles, maybe you could see a trace of something new. So that was sort of our motivation. It wasn't just antiprotons, you could also make positrons. And at the same time, these annihilations give you a whole cascade of different things, which include gamma rays as well. Anyway, so out of these deliberations, we figured out in 1984, in this paper, that, that there would be at certain energy ranges, mass ranges for the dark matter candidate, gamma rays, positrons, and antiprotons. Okay, so many years went by, and where are we observationally? So let me focus then on the antimatter. Okay, so this is a summary from a few years ago, and so people began looking. It took them probably 3 decades to gear up and do better experiments, but this happens. You have to go above the Earth's atmosphere because you're looking for particles that don't get to the ground, and you look in space, and they were both balloon and now space experiments. And so here you see, for example, the antiproton predictions, and this is the data, and superimposed is the standard background you get from cosmic rays just going through interstellar gas, and they make occasional proton-antiproton pairs. So you get a few antiprotons. So that all fitted conventional theory. But the big surprise was that first we had these huge uncertainties from the early balloon experiments, and then there was an experiment called Pamela, an Italian-Russian satellite, which measured not only the decline, this is the expectation from cosmic rays, but this possibility of a new component. Somehow, as you went to higher energy, you were seeing a new source of positrons in this interstellar medium. Now, the motivation for these satellites was, I think, at the beginning, to prove that we might be living in a universe which had equal amounts of matter and antimatter. There were some bizarre ideas that were designed to test. But over the years, it became clear that looking for dark matter was a key goal. Okay, or some other source of positrons. Anyway, so there we are, this very interesting increase. And so here is, the standard cosmic ray, and you add some new source, whatever that is. Okay, so could that be the dark matter signal? Okay, and so then here is the newest data from the latest satellite, okay, or experiment on the space station, actually. And so this currently taking data still shows you this decline in positrons, and then suddenly this very intriguing rise again. And this shows you the sort of prediction you might get if there was a dark matter component. And basically, it cuts off abruptly because above the mass of the dark matter particle, you can't make anything with any energy, okay? You're limited by the mass that collides, okay, and then annihilates. And so you expect some abrupt decline. So everyone is eagerly waiting now for the newest data to see whether, when they keep on taking data, they will actually see, they're beginning to see maybe a leveling off. Will it actually ever come down? Will it come down again? If so, would that be evidence for anything? Okay, at the same time, and this is typical of astrophysics, you have a more recent idea, it's true, but an entirely plausible idea, which says that we have lots of pulsars around us. They have these compact neutron stars. They emit electron-positron pairs, and these things could propagate to the Earth, be part of the cosmic rays, and you'd have a local source of positrons, which would then add to the standard cosmic ray source. And so it turns out the nearest pulsar, one called Gaminga, I think, and there are a few others, would be the closest and the brightest source. And this shows you the predictions. And so if you add up all these individual pulsars together, you can actually fit the data where you have a hint of this new component over there. This is the standard secondaries, and you can fit all this data with pulsars, okay? And of course, the exciting thing is, again, in the future, is someday, with better data, we will look around the sky and see where the positrons are coming from, and maybe there'll be a glow in the sky towards the nearest pulsar, telling us that that really is the source, okay? And so we haven't seen that yet, but that will be how you can test this theory. Remember, science has to be falsifiable. In this way, you can hope to directly test the pulsar and therefore kill the dark matter, the rival explanation. Unfortunately, it's not quite as clean as that, because the other big test, obviously you need more than one test to do this, is the cutoff due to the mass of the particle. And this shows you that if this is predicted data, simulated future data, if they even were to find this sharp cutoff, okay, then sadly, you could either fit this equally well with dark matter, which is natural, or with pulsars, because the pulsars lose energy by diffusion, and you naturally get a fairly sharp cutoff, depending on how those particles get to us at the Earth. Okay, here's another piece of work that came out of those early days in Santa Barbara. So the sun is now a wonderful object, obviously. It's crucial to our life, but it also is a great dark matter detector, okay? Because it so happens that these dark matter particles, as they go around the galaxy, do collect in the sun. They scatter with the outside, and they collect in the middle of the sun. And so this is sort of interesting, isn't it? Because this could be a possible way. Could you ever see them? Well, a year later, we wrote a paper saying that, yes, indeed, when these particles annihilate in the middle of the sun, and they're concentrated, they will annihilate even more than they would out there in the rest of the halo, they will produce neutrinos. Now, the sun is pretty opaque. How the hell can you look inside the sun? Well, it turns out the neutrinos of high enough energy can escape from the middle of the sun. Okay? And so the hope was, look at the sun. If you see this weird neutrino signal, that would prove that the sun, which is a dark matter collector, par excellence, beats anything you'd ever hope to do anywhere else, or on the Earth, whatever, you know, could be your ideal solution. So how does that work out in practice? Okay, so it's motivated the following types of experiments, okay? So and these are remarkable futuristic experiments that are running actually now. It's quite incredible to me to even describe these things. So they're 2 kilometers down under the ice, and a similar depth in the Mediterranean Sea. Strings of phototubes are used to look for light flashes in the dark. And what you're looking for is, as these particles annihilate in the middle of the sun, okay, they will hit the Earth, and in the Earth they'll produce muons. The muons, some will go through this detector volume, which is being examined. You'll see white light flashes, and you can even tell where they're coming from. It's like a telescope. You can look at the sun by looking, downwards. Okay, so what did they find? Well, they've been looking for a long time, and all they have are upper limits. Okay, so that's it's interesting. But the upper limits from IceCube are competitive with those that you can get from other experiments. So it's very interesting. We haven't yet seen the sun as a source of annihilating dark matter, but maybe someday. Okay. Right. Now, another aspect of this is, and this is another curious thing, is that as these particles get trapped inside the sun, they scatter with particles in the sun, and they change the nature of the sun very slightly. And so this shows you, for example, the temperature in the middle of the sun. And if I have particles entering the sun, they actually transfer energy because of their very long distance the weak generating particles can travel before they settle finally in the middle. So they soften the core of the sun in temperature. And this has a very curious effect, and some of the particles, depending on the mass, can do this more effectively than others. But the curious effect is it can really affect the one way we have of studying the interior of the sun from the Earth successfully so far by doing the equivalent of what is called helioseismology. You look for earthquake-type effects in the sun, and these give you oscillations, sound waves, and pressure waves, and gravity waves that propagate through the sun and lead to tiny oscillations on the surface that you can measure when you take, Dopplergrams of the surface of the sun. And so this whole study of helioseismology worked beautifully, and this shows you the residuals of the standard model of the sun, which we think we understand, as it was a few years ago. And then some clever astronomers went and said, we've got the opacity of the sun completely wrong. We do better modeling of oxygen in the surface of the sun. Let's change it. The opacity changed, then suddenly the model that did fit the sun and fit the neutrinos from the middle, etc., no longer worked. And so you're up there somewhere. It turns out that when you add dark matter particles, you can change things a bit. Depending on how you adjust the particles, you can either do too much or too little. So the only point of the story is that dark matter has an effect on the sun, and we don't have a good model of the sun at this time, despite the fact that it's the nearest star to us. So this goes back to the point of, how safe, how secure are we with anything to do with star formation if we haven't got a model that actually works for the sun, and that's true, and we don't, but that's part of another story. Okay, so back then to this 84 paper. And so the third prediction was gamma rays. So when you have these rare annihilations out there around us of dark matter particles, they should also produce an occasional gamma ray. Okay, and gamma rays now are being studied with these wonderful telescopes like the Fermi telescope. So what sort of signal could the gamma rays give you? Well, the Fermi telescope, when it looks at the sky, and they look here at a small patch of the sky near the center of the galaxy, they see, let's just look at this. I mean, this shows you the data from Fermi and all attempts to model it. They see an excess. So this is the excess flux of gamma rays from the center of the sun. They see too many compared to the standard model, which adds up all the interstellar contributions, all the known gamma ray sources. There are too many gamma rays from the center of the galaxy. Okay? Why is that? Well, the dark matter does collect in the middle of the galaxy. That's standard. There's no hole there in the dark matter. So maybe you should get more annihilations and more gamma rays. That is the hope. And so indeed, one takes simulations like these of the Milky Way galaxy. This is pure dark matter, and you convert this to what you expect you might think for the gamma ray flux might be. And so this shows you how the dark matter is concentrated, how there are many, many clumps and dwarf halos of dark matter, as you saw in Simon's talk previously. But what about the signal from the galaxy from this dark matter, which is going to be annihilating at a somewhat greater rate in these clumps, and especially in the center, where the most massive clump of all is? And so what does that look like? Well, this shows you the best evidence, and you'll hear perhaps more about this in the round table, that we have to date for dark matter anywhere. Okay? And this is the fact, this Fermi excess of gamma rays that I talked about in some of the galaxy can be interpreted as dark matter, and this is the excess they see. And if you try in the center of the galaxy, the central 100 parsecs or so of the Milky Way, when you take away everything else, you see this blob of extra gamma rays. And if you try to model this with, first of all, with different dark matter particle models, you can see you can get things that look pretty much like that. And if you try to fit the spectrum as well, the gamma ray distribution, also you can fit it beautifully with a simple dark matter model for a fairly lightish dark matter particle. Okay, so that is then the gamma ray story. There's one other object which I want to tell you about because it's truly, I find, one of the most exciting future developments in the field. So this is going forward from our history to what might happen next. Well, in the center of our Milky Way, there is a 4 million solar mass black hole. And so this is in itself an amazing story, and it's a gamma ray source. And it's been studied with the Hess telescope, gamma ray telescope. It gives you this very peculiar distribution of gamma rays. And there's some evidence that the gamma ray spectrum falls off rather sharply. Now, we don't know what's producing the gamma rays. It's one of the brightest gamma rays in the sky around this black hole, the center of the galaxy. So what could it be? Well, if you were to find in the future, and this is the future of gamma ray astronomy, it's called the Cherenkov array, a whole array of telescopes on the ground, very high energy gamma rays, and they will be looking to see if indeed, when they stare at the source in the center, it has a very sharp cutoff indeed. If it were to have a very sharp cutoff indeed, we don't know, then that would be a smoking gun type signal for a cloud of dark matter annihilating around the black hole, maybe. So that's for the future. Okay. And then continuing my black hole story, so the black hole has this interesting means of collecting dark matter around it when the black hole forms. And so this shows you the prediction for the inner few parsecs of the Milky Way. This is dark matter density far out, and it gets denser nearby. And you can show that within the central core of the galaxy, where this density is a bit higher around the black hole, you get extra annihilation, as you maybe saw in that prediction before. Well, is there anywhere else that you might want to look for this apart from our black hole? Well, where would you look? Well, it turns out that what you expect to find depends very strongly on the mass of the black hole. Okay, so the more massive the black hole, the more flux you get. And it so happens that if I go to the next biggest, well, in fact, the next big black hole close to us, which in fact is 1,000 times bigger than our black hole, you get an immense possibility of finding this cloud of dark matter around the black hole. This is in the galaxy M87. Okay, so this is an interesting thing for the future. You could expect gamma rays from the black hole there, and that's people have been looking with the gamma ray telescopes at this galaxy. But the basic point is this, that this is the black hole in the center of the galaxy. Here's a jet. So you have a natural jet. It's nature's particle accelerator. Okay, here's the black hole, cloud of dark matter around it. Who knows what we might see? Okay, so this is a prediction for the future when we get bigger and better gamma ray telescopes and other types of telescopes to zero in on this distance. Okay, and my final black hole remark is this. So now imagine, and this is even looking forward to the more distant future. So here's a black hole, okay, and there are particles of dark matter coming in and orbiting around the black hole. Some go one way and some go the other way. Okay, so they're going to collide with each other near the black hole, okay? And it turns out that if you go through the energy they can achieve, it's not terribly interesting. It's a few times the rest mass of the particle, but it's a possible interesting, it could lead to an interesting gamma ray source, but it so happens that you can do much better. So, because there's this wonderful process called the Penrose effect, which says that if I have particles falling into a black hole, pairs of particles, with some maybe emitting light, then if something falls in to the black hole, I can get more energy coming out in the opposite direction, okay, depending on the debris that comes from this decaying particle, for example. So if I have a decay, bit goes in, bit goes out, but to conserve energy and momentum, it turns out that I get a big boost called the Penrose effect because of the rotation of the black hole, basically. You can tap the black hole. It's maybe the most wonderful accelerator we have in nature, and it's thought to be behind all of the jets or energy phenomena we see in quasars, everything in astrophysics. Basically, ultimately, it's connected to this plus a little bit of extra astrophysics, sure. However, it's been highly criticized because it turns out that this is how the effect might work. You have a particle falling in, but it's been criticized because, because it turns out that what Bob Wald showed was that you can never actually achieve this in practice because, if something decays, only some fraction of the energy falls in, and you'll never get a big boost. Everything gets so redshifted. But the miracle that we think could occur is if I go to this rotating black hole and you figure out how much energy these particles might have, then they can be really, really large, up to infinite even. And so this means that you can suddenly have a way of putting extra energy into this Penrose mechanism. Okay, there's no maximum, and you can expect gamma ray lines and all sorts of weird things. Okay, so final remarks. When I began in this field, I worked a lot on background radiation. And so I worked on the diffuse background, and other people worked on other backgrounds, ultraviolet backgrounds. and and discrete models, all backgrounds like a huge garbage pool for all the energy that comes out in the universe. So you can see everything if you look at the background radiation. And we were dubbed the background brigade in those days by one of our critics, and this was thought to be one of the ways, okay? And the gamma ray background, etc. So the gamma ray background is over here. This is the gamma ray background, and you can see very high energies measured by the Fermi satellite. These are known sources, and so there are all sorts of wiggles and things in it, and you might wonder if there's some region, some possibility of exotic dark matter signals. We don't know yet. That will be for the future too. So in conclusion, let me just put on my crystal ball and say this shows you where we are in the space of parameter space of all future experiments. And so right now, this is about as far as we've gotten in terms of the possible searches for dark matter. With the LHC, and developments thereof, we'll be pushing in this direction to get to lower and lower rates, higher and higher masses. And with experiments like the Cherenkov array, we'll be pushing in this direction. And so then I would say that following our progress in particle physics, we're likely to need to push to very high energies to understand more about supersymmetry and possible production of dark matter. And at the same time, we have this wonderful new developments in gamma ray astronomy, which will take us up to these very same energies too, tens of TeV. So the future may well be to push to very high energies, very high masses for possible, but we haven't got there yet. Okay, thank you.
Thanks a lot, Joe, for this very nice